Stanford University.
All right, guys, welcome to CS 193 Lecture 15. Kind of done with our little interlude of guest speakers from Apple, so you kind of stuck with me and Al again for a few days here. Today we're going to talk about device APIs. And this is actually some really cool and exciting stuff because, I mean, we've got these really awesome new devices that have a lot of different sensors and different input devices on them. And the only thing we've really talked about so far is the touch screen for multi-touch input. But we've also got a camera, we've got an accelerometer, we've got a compass. There's a variety of different input mechanisms that we haven't even gotten to yet. So we're going to talk about those today. And then we'll end up speaking a little bit more about power management, because starting to use all these extra pieces of hardware is going to very quickly begin to be a drain on the battery. So we'll talk about ways that you can use these additional input devices, but use them smartly so that you can have them turn off and power down and go into power saving modes when you don't need them, so that your battery life can last as long as possible for your users. Because you don't really want them to start playing your game and be able to play for 5 minutes before it's dead. All right, so a few announcements first. The Paparazzi 4 assignment is due this Friday. We had previously said Wednesday, but we were a little bit late getting it out. So this Friday is the due date for Paparazzi 4. And the late days, this is the last assignment that can use the late days. So if you still got them, just hang on to your assignment and don't turn it in until late. Turn it in whenever, but if you've got them, use them now. And get started working on your final projects. We started sending out emails about them. If you haven't received one yet, certainly we'll be getting to you soon. But if you haven't gotten one yet, send us an email. I think we've gotten them all out at this point, responses. I think so, anyway. Yeah, we'll double check. But you probably, what's up? Yeah, most of them should already have been sent out. So get started on that. Today's topics, as I said, hardware features. Oh, yeah. And I didn't put an announcement up there, so I forgot it. We are actually running this course again in the spring now. It's a kind of late last-minute plan. We're just adding it to the schedule now. Our esteemed TAs here are not available for the next course run. So we're going to be looking for some new TAs for the next session. If you have an interest in that, get a hold of us, send an email to the class list, and we can get you more information about it. But we are looking for 2 more. So, if you want something cool, I'm sure these guys can tell you how exciting it is. And, talk to Paul. He's done it twice now, so clearly he came back for more. It was exciting enough the first time. All right, so today's topics. We're going to talk about hardware features, as I said, camera, location, accelerometer, compass, and the battery life and power management. All right, so kind of already went through a lot of this, but we'll do it real quick. Hardware, the camera's on the back. I'm sure you can recognize that's maybe not the most up-to-date photo of an iPhone that we've got, but same basic idea. We've still got the camera on the back. And now, in addition to the still camera that we also have a video camera in the iPhone 3GS. And we'll talk today about how you can use both the still and video cameras to capture photos and video and use them in your application. We've got core location. Core location, we've mentioned briefly and talked a little bit about it, but it's a new framework on iPhone OS that lets you track the user's location and the location of the device. And we'll get into the 3 modes and methods that it uses to figure that out, and how you can use that on your own to figure out where the device is. This is independent of the MapKit framework. MapKit does, in fact, use core location, but you can use core location independent of MapKit. So MapKit is the framework that shows Google Maps, and you can use core location to track the user's location on there. Core location is a lower-level framework. It's not a user interface framework that just tracks user location and gives you raw data about that, but it doesn't include any user interface elements. So you can use it if you don't want to display a map, but still want to do tracking of location. And then we'll talk about the accelerometer and the compass, which let you track the orientation of the device and the direction that it's facing relative to either magnetic or true north. And all of these things, as I mentioned, are hardware features, right? I mean, they actually require actual physical hardware to figure out the orientation of the device or to get a GPS signal. And Macintosh computers generally don't have all those things. So not all of these features are supported in the simulator. As we talk about all of them, I'll kind of point out which ones are and are not available. And some of them have more features available in the sim than others. But for the most part, when you're dealing with a lot of these things, you probably want to use a real device. especially when you're talking about things like the accelerometer. If you're trying to develop a game that has tilt sensors for steering, it doesn't make a whole lot of sense to develop that in the simulator because you're probably not going to pick up your Mac Pro and shake it back and forth in order to drive. So a lot of these things you'll probably be dealing with actual on-device development. All right, so the first thing we'll start out with is the image picker. And the image picker is going to be your interface to both the still camera, the video camera, and photos that are on the device synced from your Mac by the user. So if you're, or your PC actually. So if your user is using iPhoto on the Mac, or actually I'm not sure what apps on Windows, maybe a folder full of photos, I guess, and they get synced onto your iPhone, the user has their whole collection of photos on there. You can get to any of those photos and use them in your own application. You can ask the user to take a new picture, either a still one or a video, and you can, there's standard user interface that'll come up. It's basically the camera user interface from the camera application. And you can present that, ask the user for a photo, and then use that photo to draw some, I don't know, beards or something on your friends. So the camera interface looks kind of like this. As you can tell, I was working on this afternoon with the bright lighting around that picture there. But that is basically the camera interface. It's got, well, not too much. A big screen that shows you the image that the camera is capturing right now. There's a cancel button, which lets the user dismiss it, a photo button to take the picture. This doesn't show it on this picture, but there's also a toggle switch that you can allow the user to pick between still or video. And when you present it, you can pick whether they can see just the still camera, just the video camera, or choose between the two. So we'll talk about that. The Save Photos album is, it's basically the place that you can get photos that the user has already taken with the camera. So if your user has taken some pictures when they were running around hiking up the mountains, and you want to let them edit it later, those are going to be stored in the Saved Photos album. They're photos that were taken on the device but haven't been synced back to a computer yet. So you can get to those. And you can also get to the photo library, which we already talked about. This is the library of photos that the user synced over from iPhoto or from their computer. And as you can see, the Saved Photos album is actually the first item up there in the photo library. So those are basically your three sources of photos using the photo picker. So the code for that is actually pretty simple. There's two classes, well, one class and a delegate protocol that you use in order to access these things. The class is the UI Image Picker Controller. And UI Image Picker Controller is a subclass of UI View Controller. It's actually a subclass of UI Navigation Controller, but it's a little odd. Generally speaking, and I think we talked about this before, when you're writing your own code, you're probably not going to subclass UI Navigation Controller. It's not something you need to do very often. But yet we've talked about 2 or 3 cases so far in UIKit where we have subclasses of Navigation Controller. Do what we say, not what we do. But yeah, so UI Image Picker Controller is it's a View Controller subclass, so you present it modally. The user takes a picture, and when you're done, you dismiss it. It goes away. You probably wouldn't be pushing it on your own navigation hierarchy because again, it's kind of a modal thing. You want the user to do some action, and they can't really do anything else until they're done doing that action. So yeah, so present and dismiss. Handles all the user and device interactions. You don't have to worry about the specifics of how the camera works or what the photo formats are that the camera, the raw data it's giving back. The low-level frameworks handle all that, and you end up getting a photo from it. There's the UI Image Picker Controller delegate protocol, which we've talked a lot about delegates so far. Basically, you'll register your view controller or whatever observer object you have as the delegate of the image picker controller, present it modally, and there's delegate callbacks that you'll get when the user either takes a photo or cancels taking the photo. So there's really only 3 steps, just 3 things you have to do to use this. The first thing is you want to check to see if the source that you're interested in is available. So some devices don't have a camera. iPod Touch doesn't have a camera. Some devices don't have a video camera. Only the iPhone 3GS has a video camera. So if you're interested in a particular type of image or asking the user for a particular source, you first want to verify that that source is available. And there's some API that we'll look at that let you do that. Once you're sure that the thing that you're interested in is available, so if you want to know about taking a video, you've made sure that the device you're on actually has video capability, then you want to assign your delegate object after you allocate your UI Image Picker controller, and then present that controller modally. So there's really, it's pretty easy. Basically, the code will look something like this. We'll call UI Image Picker Controller is source type available. And that's actually a class method, so you can call it even before you've allocated your Image Picker controller. So you just check to see if the source you're interested in is available. In this case, we just want to know if the device has a camera. We don't necessarily care if it's video or still. We're just going to check to make sure it has one so that we won't do this code on an iPod Touch or in the simulator. And then we'll call UI image picker controller alloc init to create our image picker controller. Set the source type to camera, since we want a camera as the source, not the photo library on the device or the recent photos. And we'll set ourselves as the delegate so that we get the callbacks when the user either takes the photo or cancels. And then we'll just present modally. And animated yes, you've seen this pattern a lot. We probably want it to slide up, so we'll call animated yes. Oh yeah, probably should have clicked through that, huh? There we go. All right, so once we've done that, the user is going to get something like this. Actually, it's going to look more like that first one I showed you. I didn't update this image, but it's you get the camera, and the user can take the picture or cancel it. Once they've actually taken the picture, they'll have the option to crop it, so they can pinch or pan around in the image to choose a particular portion of the image that they want. They can do this for all the different source image types. So if there's something that's already stored on the device, and they just want to actually like the face to be cropped out, you can kind of see this in the address book. When you're picking a photo for your contacts, you probably want to zoom in on an existing photo that you have to make the user or the person's face fill the entire frame. So they can do that and then choose or cancel the photo at that point too. And we'll see in a little bit how this works. But you basically get both the cropped image and the original source image with a rectangle specifying which portion was cropped. So you can, if you don't care about the rest of the image that wasn't cropped, you can just use the image that we give you, which is already cropped down to the size the user asked for. Or you can get the whole thing and do something else with it. All right, so in your delegate object, you're going to have two methods that you can implement. And that's, as I said, defined by the UI image picker controller delegate protocol. Things get a little bit long and wordy, but there you are. So you've got the image picker controller did finish picking image with editing info method. And we'll get into the editing info in a little bit. That's going to be the way that we tell you about this cropping. So it's not super important in all cases. You may not necessarily care about it. So we'll skip that for a second and just talk about the first two. So image picker controller, obviously the first parameter tells you what the UI image picker object was that did the picking. And did finish picking image, you'll get back a UI image that is the image the user took. So that's all you have to know about the camera. You don't need to know specific details of the formats. You just get a UI image back. You can write it to a file, do anything that you would normally do with a UI image. These are pretty big images, though, so you kind of want to keep that in mind as you're working with them. The cameras are pretty high resolution, and the images that they produce are quite large, and they take up a lot of memory. So you probably don't want to end up hanging on to like 10s, 20 images in memory at once. You're going to start getting memory warnings, and pretty quickly going to get your process killed if you don't take care of those memory warnings. And then the second thing there is the image picker controller did cancel. And this will be called in the case where the user actually hit the cancel button rather than taking a picture. And in both cases, you actually want to slide the sheet down. But in this case, you won't get an image because the user didn't actually take one. So you'll just be told that it was canceled. All right, so let's implement those. The first one is the image picker controller did finish picking image editing info. And this is the case where there was actually success, right? The thing came up, the user took a picture, and they presented or clicked all the UI to make it so that they selected that image. So the first thing you'll do is save or use the image in whatever way you want. Write it out to disk, or put it in memory somewhere else for you to draw some faces on it or something. And then you'll dismiss the image picker. So this part's actually pretty important. The delegate protocol defines that it will call this method for you when the user picks an image, but it won't automatically dismiss the controller. You have to do that yourself. So you'll want to call self-dismiss modal view controller animated. And again, animated yes, so it slides down. And assuming you didn't already release your picker before, you'll call picker release to clean up your memory usage. I keep forgetting I have these highlighted. All right, so the next one then is the cancel case, and this one is even easier, right? We just do that last part of dismissing the modal view controller and releasing the memory for the image picker controller because the user canceled. They didn't actually want to pick anything. There's no image. There's nothing to do. Just make sure that the UI goes away and that we clean up our memory. Sorry? Yeah?
So, should image picker controller be used only as a modal view, or can it be used as a permanent view controller?
As a, sorry, permanent view controller?
Yeah, just normal.
So the question is, should the image picker controller be used only modally, or can it be used as a permanent view controller? It's really intended to be used as a modal presentation. I suppose you might be able to come up with some user interfaces, and we'll talk about this in a little bit. There's some new features in iPhone OS 3.1 that allow you to do some of these more augmented reality kind of apps, as a pretty common thing happening these days. And in those cases, you're displaying the image from the camera and adding extra layers on top to display some additional information. So in that case, you might actually have it as a permanent part of your application rather than being a modal thing. But I think in most cases, it's probably being presented modally, especially if you're asking the user to specifically pick a photo. If the user interface of your application is the video camera stream with user interface on top, then maybe it's a permanent part of the UI. But if you're asking the user for a photo, it's probably modal, so that the user picks their photo, they do the operation, and it goes away, and they're done. That make sense?
Yeah, but anyway, it's a general UI view controller, so we can put it as a normal UI view controller, right?
Yeah, so the question is, it's a normal UI view controller. Can you just use it as a normal UI view controller? And that's true. You can pretty much do anything with it that you could with any other UI view controller. But I think sort of standard practice and convention in some cases leads us to use particular UI view controllers in one way rather than another. Like the people picker view controllers are generally pushed onto a navigation stack. Sorry, not the people picker. The people picker is usually presented modally because you're asking the user to pick a person. The address book like new user view controller is usually pushed onto a navigation stack because you're viewing the new user. Sorry, I keep calling them the wrong thing. I don't remember the names of the address book view controllers. The one where you view a person is usually pushed onto a navigation stack because you're viewing that person, but it's not a modal session. You generally are you've got a list of users and you're navigating into it, and then you're going to navigate back. That one by convention is usually presented on a navigation stack. They're all just UI view controllers, and they technically can all be used in pretty much any of the standard configurations view controllers can be used in. But I'd say there's kind of preferred usage patterns for some of them, and the preferred usage pattern for this one is generally modal presentation. But there's nothing that prevents you from doing other things with them. They're just view controllers. All right, so in the case where the user actually picked the image, we've got the long method name that I've already forgotten. So if we want to allow the user to edit the resulting image, this is going to be that editing info dictionary that was the last parameter on that method. So when you allocate your UI image picker controller, there's actually a method called allows image editing, sorry, a property that you can set to yes. And that's what defines that the user can then pinch and scale and move around the image to pick different parts of it. So it allows the user to crop it, and this cropping metadata is returned in that editing info dictionary. So yeah, that's going to look like this. We already saw that picture. So the editing info dictionary is that additional property there. The original image, there's actually two keys. The original image is going to be under the key UI image picker controller original image. And this, again, is a UI image that has the entire original image. So it's pre-cropped. It's the entirety of the image. And then the second thing is the crop rectangle, which will be under the UI image picker controller crop rect key. And that key actually contains an NS value that wraps a CG rect. So you can pull that out into a CG rect. And basically, it's the rectangle in the source image that the user cropped to. If we go actually back here for a second, the did finish picking image part, the UI image that you get back in the delegate method, is pre-cropped, right? So it's not the full image. It's cropped down to the size that the user actually picked. So if you need the full image, you actually have to get it out of that editing info dictionary. So I kind of mentioned this augmented reality concept. There's a couple of new, actually 3 new properties on UI image picker controller in iPhone OS 3.1 and later, which enable a lot of these augmented reality style apps. And I keep saying that, and I've kind of glossed over it a little bit. I've got a picture here of one of this kind of thing in a second. But basically, you've got 3 options. The first is shows camera controls. And this option basically determines whether or not the standard buttons for the camera are visible. So by default, you've got that cancel button, and you've got the take photo button. And if you're using the still versus video camera, you've got a switch to decide whether you're using still or video. If you set shows camera controls to no, all that stuff goes away, and you'll basically just have the raw video on screen, and that's it. So once you've got that raw video, you might want to present additional user interface on top of it. And that's what the camera overlay view is for. So this property lets you assign any UI view to be displayed on top of the camera video. So the camera feed gets displayed in the back, your view goes on top, and you can add any additional controls or whatever subviews you want to overlay on top of that. So A lot of apps are starting to do interesting things where the user is pointing in this direction and they're seeing the camera feed and they're displaying some additional info about what the user is looking at. So if you point it at a building, it overlays some info about what that building is, figuring it out from your GPS and compass and the direction that the user is looking at with all these other things that we'll talk about in a minute. So camera overlay view is what does that. And then the last one is the camera view transform. It's a CG affine transform. We've seen CG affine transforms a couple times. You may not have used them too much yet. The common case you probably saw, and we talked about a little bit, was on UI view. A view has a transform property, which is a CG affine transform that lets you either rotate, scale, or translate of the view itself. So you can do the same thing using the camera view transform to the camera image, which will basically apply either a scale, rotation, or translation to the actual raw camera video that's being displayed. So you can move it around or position it at a different part of the screen or just part of the screen if you're planning on displaying extra UI around it. So those three things actually give you a lot of control over the kind of things that get displayed if you want to do this kind of user interface where displaying the video feed from the camera is a main part of your user interface. So this is kind of an example of one of the apps that does this kind of thing. They're showing their camera feed in the back, and then it's a barcode scanning app. So it puts a bunch of user interface on top that sort of shows the user where to aim the barcode. And it'll, actually there's another property. I don't think I actually even put it in here. There's another method called take picture on UI image view, UI image picker controller that lets you programmatically take a picture. So the user doesn't actually have to press a button. You can programmatically take a picture. And if you do that sort of in intervals, you can analyze the picture, the frames, as you're going at discrete points. All right, so we kind of mentioned this already briefly, but just want to reiterate it because it is pretty important. These photos are pretty big, and you really don't want to hang on to too many of them in memory at once. So if your user's taking a bunch of photos and your app relies on getting 20, 30 photos from the user, you're probably going to have to start writing them out to disk at some point because you just can't fit them all in memory. So if you have to start writing them out, there's a couple ways you can do it. If you're just trying to write them out for your own application use and you don't want to have the user get access to them some other way or sync them back to their computer, you can just write them to a file yourself or store them in a core data database or do something like that. But if you want the user to be able to copy them back to their computer, so say you take a picture and then modify it by putting a hat on someone's head, and then you want to allow them to sync that back to iPhoto on their computer so they can send it to their friends or do whatever from their Mac. There's a function called UI image write to save photos album, which takes a UI image and a couple other parameters that we'll talk about in a second, and actually saves it to that save photos album we talked about. So it's the first one that contains all the photos that were taken on the device. You can write your own photos to that save photos album, and then they can be downloaded by the user onto their computer. The other parameters I mentioned on this are the information you need for an optional completion callback. So it's an object that's the target and a selector to be called when the write happens. This basically lets you do this write asynchronously. Writing one of these photos out to the flash can be quite slow, actually. It can take well over a second. So you probably don't want to just call this on the main thread and block the main thread. But since it's such a common thing to do and a lot of people are going to want to be calling this, rather than have to do all the threading yourself, there's this completion callback that you can set up, which basically tells it to go off and do the writing on another thread for you and then call you back when it's done. There's a similar function to be used for writing video, along with another one that tells you whether a particular video is actually allowed to be written. So there's the UI video at path is compatible with saved photos album function. And you can call this sorry. You can call this on with a path, and it'll check to see whether the video at that path is in a format that can be written back to the saved photos album. And you probably want to do that before you try to write something, because otherwise writing it's just going to fail. Then you've got the also excellently named UI save video at path to saved photos album function, which writes that video out to that same to that same album in the photo library that the user can then sync back to their computer. And videos can be downloaded, and again, there's this optional completion callback, so you can do it asynchronously. Writing a video is even slower than writing a photo because it's much bigger. So you probably want to do this asynchronously so you don't block the user from doing other things while you're doing it. Both of those are actually available in the simulator. The camera is not. You can't take video. You can't take video and you can't take pictures from within the sim. But you can get the Save Photos album. You can write to it. You can read from it. There's actually a stock set of sample photos that come with the simulator. I think it's like somebody's graduation and someone's vacation, and I don't know. You can kind of feel like you're a part of their life. It's pretty nice. So those are right on there. You can do all this in the sim. So if you don't need to actually use the physical camera, you're pretty good to go to test that in the simulator. Although, again, be careful, because the simulator has way more memory than the device, because it's using all the memory that's available on your Mac. So just because you're not having memory issues in the sim doesn't mean you won't have them on the device. And the same goes for performance. I mean, this computer's way faster than the iPhone. All right, so we kind of covered all these points. I just want to put them together in one spot because they're all pretty important. So using image picker controller effectively. So always check that the source type that you're interested in is available. You don't want to fail to check this and have things just silently fail for the user when they're on an iPod Touch. If part of your application is, it's super important that you have a camera because your app just can't work without it, check the source availability first and notify the user gracefully that it's not going to work on this device if they're on an iPod Touch. Your delegate methods do the cleanup. So remember, if you've presented your modal view controller and you're getting your delegate call back, but your photo picker's not going away for some reason, it's because you haven't actually dismissed it. It doesn't happen automatically. You have to do it manually. Be frugal with images. Don't store too many in memory. And yeah, it is available in the sim. All right, so that's pretty much all there is to image picker and getting images. And you can actually do quite a lot with just what's there. And it's pretty powerful. And there's some really cool apps already that are doing a lot of stuff. So come up with the next cool one. So let's move on to core location. This is also pretty cool because it lets you do all kinds of interesting things. If you've been using the Stanford app at all, you've seen that they actually show you your location on the map. And it's not even one of the Google Maps. It's an actual map of Stanford that's quite detailed. And they track your location using core location to do that. And you can do all kinds of interesting things with this. You can track the user's motion over time if you're trying to track their jog path and give them information about where they went, how fast they were going, all that kind of thing. You can do that all with core location. So we kind of already saw it in use in the Maps app when Brad talked about it. Actually, I think it was Brad, right? Yeah. Well, anyway, we talked about Maps. And sorry, Al talked about it. And we saw the user tracking their location on the map. And that's pretty cool, but you didn't really have to use core location in order to get that to work because it's provided for you by MapKit. So let's talk a little bit about how this actually happens. Oops. So there's three main methods for tracking location, and Al talked about this, so I'm going to go over it just real quickly. There's the cellular network location, which is a very broad way of finding location. It's not very accurate. It's within a very wide distance. There's with the Wi-Fi location, which can tell you based on what hotspots you're close to, where it thinks you are. And Al talked about some of the issues with that when he moved to a base station to his sisters in Canada, and it forgot where he was and thought that he was still in California or something. And then finally, there's the GPS, and this is obviously the most accurate. And core location actually wraps all three of these, so you don't have to know specifically about which one you're interested in order to use all of them. We'll get into some specifics about how you can kind of hint to core location which one it should use. But basically, you determine how accurate the location information you needs to be, and then tell core location, I need to know where the user is within 100 meters. And core location will pick the appropriate technology to make sure that it gets you the information as accurately as it can on whatever device it can. So you don't even necessarily have to know that you're on an iPhone which has GPS or an iPhone which doesn't. It takes care of that for you. So there's all three of these, and core location puts them all together. Oops. Come on. So core location is the framework that does this. And like we've seen with a lot of the other frameworks outside of UIKit and Foundation that we've been using, if you want to use core location, you actually have to add it to your project. That seems to come up. We've come across it in MapKit. We've come across it in Core Data. If you start using these functions or any of these things that are in other frameworks, you actually have to add them to your project yourself because they're not added as part of the standard Xcode template. So core location defines two classes and one protocol that are used to figure out where the user's at. So the first class is CO Location Manager, and this is basically the main entry point. It's the object that's going to be your interface to all of core location. And then the other object is the CO Location, and CO Location defines a particular location, a discrete instance of where the user is at a particular time, at a particular latitude and longitude, as accurately as it could figure out for that particular time. And then the delegate protocol, CO Location Manager Delegate, is basically the way that you interact with the CO Location Manager, and it's the way that you're going to get these CO locations from it. So let's take a look at this. There's two optional methods on that delegate protocol. There's the Location Manager did update to location from location method, and that will be called when a significant change has occurred in the user's location. Significant kind of being defined as significant for the particular source type it's currently using. So you'll get the updates more often on GPS than you will on cell network, because it can't necessarily track your location as effectively or accurately on the cell network. And you'll get those two CL location objects. The new location will be time-stamped for the current time, the old location for the last time that it had location information, so you can kind of tell how long it's been since the last notification you got about it, and you can figure out the distance between them. One interesting thing about this is that it's actually location-based notification, not time-based. A lot of other notifications of this type will give you callbacks at discrete intervals. So every certain period of time, it'll say the user's here, user's here, user's here. And it may keep telling you that even though the user's not moved anywhere. Core location only calls you back if the user's actually moved. It's location-based. So if there's no movement at all, you won't be getting any notifications of anything. The reason that's important is because you want to make sure not to drive anything important in your UI off of getting callbacks, because you may not be getting callbacks. So if you need to, pulse the dot to show that the user is here, you don't want to do that pulsing as a result of getting the callback. You want to just set up a timer that does that on some interval, because you won't be guaranteed to get these at any particular interval. So that's the one for success, where you actually got a location. What about failure? There's this location manager did fail with error method, and that's going to get called if for some reason the device can't figure out where the user is. So let's say that you've got your phone and you're driving through a tunnel and you're underwater somewhere. Probably no Wi-Fi in that tunnel. You're certainly not getting a cell signal, and you probably don't have access, line of sight to a GPS satellite when you're underwater. So yeah, that kind of case is going to give you a did fail with error, and you'll get that callback to let you know that the device just doesn't know where it is. It can't possibly tell you. And there are some other cases where you can get this error. There are errors defined in clerror.h. You can kind of open that up and check it out. There's I think 4 or 5 different error cases. But in every case, you'll get this method called location manager did fail with error, and the NS error will include some information about why that failure happened. Oops. All right, so if you want to start using this, the first thing you have to do, as I mentioned, is use this CL Location Manager object. It's your entry point to the entire framework. So you'll call CL Location Manager alloc init to get a new one. Set its delegate, so you'll probably set yourself as the delegate. And then call start updating location. So start updating location tells it to begin generating these notifications, tracking where you are, and notifying you. If you just allocate it and set your delegate and don't call that, nothing's going to happen. So yeah, you won't be notified. Make sure you call start updating location. Once you've done that, you're going to get this callback. Location manager did update to location from location. And there's a couple of things you can get out of the location. There's actually more than a couple. There's quite a few. One of the interesting ones here is probably the coordinate in latitude and longitude. So you'll get new location.coordinate.latitude or longitude will tell you exactly where you're at. And then I also mentioned that you can figure out how long it's been since the last notification you got. So there's actually a timestamp property on a CL location, because there's one generated for a new one for every particular notification you get. They're actually also timestamped. So new location.timestamp is the time that that location was generated, and you can get time interval since now is a method on I guess it's an NSDate, I suppose, right? Must be an NSDate, yeah. I think time interval since now is a method on NSDate. So that'll basically tell you how long it's been, the NS time interval, since that location notification was generated. So if you wanted to find out how long it was between them, you could get new location.timestamp and old location.timestamp and get the difference. This just tells us how long it's been since that new location timestamp was generated. And in this case, we're going to filter out ones that happened in some period of time. But you could do other things with that. Just find out how long you've been in one spot, for instance. And then there's also the horizontal accuracy, which is especially interesting because it kind of gets back to this are we using cell or Wi-Fi or GPS? So the horizontal accuracy is going to tell you how confident core location is in the location it just told you. In this case, we are going to filter out any notifications for horizontal accuracies less than 100, and this is in meters. So anything less than 100 meters is probably going to have been generated from a cell tower, because that can't really be accurate to that, anything approaching 100 meters. So we'll filter those out by checking out the horizontal accuracy. And as the core location starts to generate more accurate information, so it starts out generating cell tower information, then it moves down to Wi-Fi, and then finally GPS. Once the satellites are found, it'll send new updates every time to let you know that it's got more accurate information. You can find that out by checking out the horizontal accuracy. There's also heading information available. This is new in iPhone OS 3.0 or 3.1, I forget, and actually only available currently on iPhone 3GS, where there's a magnetometer. But basically, it lets you know what direction the device is pointing. It's basically a magnetic compass. So you can both get true north or magnetic north, depending on which you're interested in for your particular application. But basically, you'll get the location manager did update heading method will be called. And you'll get, in this case, the true north. So heading.trueHeading will give you true north. And this is always relative to the top of the device. So if you're holding your device flat on your table and you've got the home button down at the bottom, the heading is going to be relative to the top. Even if your application has been rotated and you're in landscape orientation, the heading that you get back from the CO location manager is always relative to the top of the device, meaning the physical top, not the current rotated top. So just keep that in mind if you're trying to use the heading information while you're in landscape orientation. You have to manually rotate yourself if you want to be pointing up in landscape. So there's a couple of interesting things about the CO location manager that kind of help you to manage some of your power usage, right? You really don't want to be leaving these things on all the time. The GPS is incredibly expensive. Wi-Fi is also really quite expensive. And even the cell is not cheap. You don't want to be wasting too much power by checking for location information when you don't actually need it. So you probably want to, there's two basic things that you want to do. The first thing is you want to define the accuracy level that you need for the location information. So there's a property on Location Manager called Desired Accuracy that lets you specify how accurate the location information you need is. And there's a bunch of constants that you can use to figure this out. It's just defined in meters, so you could also specify your own value. But it's the CO location accuracy, and then there's best and a couple of others that you can check out in the headers. Best is actually the default. So by default, it's going to be trying to use GPS if it's available. So if you really don't need that kind of accuracy, so if you're doing like a weather app that just needs to know sort of at a large geographical scale where you're at, you just want to know you're in the Bay Area, but you don't care that you're on Stanford's campus in this room, you might want to scale that down a little bit so that the phone won't end up having to start up the GPS and the Wi-Fi in order to figure out where you're at. It can just use the cell tower. So set that in order to try and conserve some power. You also want to, hang on, we already talked about that. You also want to stop it when you don't need it. So there's this begin generating update location, or start generating, or start updating location. There's an equivalent stop updating location. So if your application has some screens that require location information but others that don't, then you probably want to turn off location updates when you're not at a screen that needs them. So if you've got some view controller that's actually displaying users' location, turn on location updates in view will appear and turn them off in view did disappear, or view will disappear, or something like that, so that we actually only have these pieces of hardware powered up when the user's actually at something that's going to need this information. If you need to, well, we talked about this already a little bit, but the user, one of the other cases that can generate an error is the user explicitly saying that they don't want to allow location information to be used in your application. The first time an application that requests the use of the core location framework is used, they're going to get a pop-up thing that looks like this, saying, "We'd like to, your application name would like to use your current location." And the user has the option to choose either yes or no to say whether it wants to do that. If it says no, you're going to get that error callback instead of the success with the location information, because the user explicitly said, "I don't want this application knowing where I'm at." So you probably want to check for that. Even if you don't think your application is going to be used in a place that won't have the availability of location information, the user can actually prevent that location information from being available. So definitely always check for the error code. It is a per application thing, so that the user has said in one application that they're okay with location updates being available, it doesn't have any bearing on your app. They're still going to be asked about your app when they first launch it. Yeah, we already talked about the location being unavailable. There is really no support for this in the simulator. Core location is not something you can test on there. There's no GPS on the computer. There's Wi-Fi, but there's no cell, so it's just not going to be there. You pretty much have to test this on a real device if you want to be using core location. All right, so that's kind of how you get a broad sort of global overview of where you're at. But what if you care about something much more local? So you've got your device in your hand, and you want to let the user drive, tilt their device left and right to be like a steering wheel, or anything else that you might want motion interaction with the device. So that's what the accelerometer is really going to get you, and also kind of the compass, which we talked about already, but that one's over in core location, the accelerometer's over here in UIKit. Yeah. So what's the accelerometer going to do? What is it? Well, it measures changes in force. So as the device moves, well, let's start out stationary, right? So you're holding your device in your hand, up and down, kind of like this, right? There's a constant downward force right now, right? The force of gravity. And the accelerometer will report that as 1g pointing downwards. If the user then turns their device to the side a little bit, that's going to change, right? Now there's going to be acceleration in two directions. And it's basically, there's a device in the phone that is measuring this acceleration. So as you're actually tilting the phone, you're tilting the device, and it figures out the new acceleration and what direction you're pointing in. So that's just if you're holding it still. But if you start moving, then it's actually going to be able to report the movement both horizontally, vertically, and back and forth in all four orientations, or 6. So yeah, what are you going to do with this? Well, the most basic use case, and you've seen this all over the phone and the iPod already, is to detect that the user has rotated and rotate the UI from portrait to landscape so that it's always face up in whatever direction the user is holding their phone. You don't have to do too much with the raw accelerometer data in order to do that. In fact, you don't have to do anything with the raw accelerometer data in order to just do these rotations. So we'll talk about some of the APIs for that. And that's the most basic case, right? So users got their phone, they're in iTunes, they've got their now playing screen up, they turn the device to the side, and now all of a sudden they've got cover flow. The UI has changed to be something that's appropriate for the new orientation that the user's holding the device. So it's pretty raw, right? It's either I'm up or down or left or right. It's not using the instantaneous feedback that you can also get. So we'll get into that a little bit later. But this is interesting just on its own. So we can basically figure out the physical orientation. Is it flat on the table? Is it flat upside down? Are we holding it up and down? Is it portrait? Is it landscape? We can figure out those things. There's kind of a duality of things here. It's a little weird. So bear with me for a second. You've got two basic concepts of the orientation. Oops, and I just flipped to the wrong place. There we are. So you've got the physical device orientation. So in this case, let's say I'm holding it like this. I'm portrait. If I'm holding it like this, I'm portrait upside down. And if I'm doing this, I'm now landscape right, because I've taken the device and I've rotated it to the right. So I'm now device orientation right. However, there's a second thing here, which is the user interface orientation. So user interface orientation is basically the status bar orientation, and it's what's happening on the screen. So just because I've turned my phone sideways doesn't necessarily mean that the user interface has changed, right? Some apps don't support rotation. So if I start out in device portrait and then rotate to device right, I'm now at user interface left because the device has moved to the right, but the interface has moved to the left to accommodate. So it's a little weird and kind of odd at first, but if you stop and think about it for a second and just look at it, it starts to make some sense. But so there's two slightly, I mean, they're directly tied together, but not necessarily, well, they're not really directly tied together. There's these two things, the device orientation and the interface orientation, and they may not be the same, and in fact, in a lot of cases are not. There's also more device orientations than there are interface orientations. Device can be just flat on the table or flat upside down. There's no corresponding interface orientation for that because that doesn't really mean anything. The interface orientation is either portrait upside down, landscape left, or landscape right. The device can be any of those plus flat on the table and flat upside down. So this is kind of an old example. It's not true in iPhone OS 3.0 anymore, but easier to explain with this than with some other things. So if we go into the Photos app and open up one of these albums and then actually go in and look at one of the photos, we're now in both device orientation portrait and user interface orientation portrait. If we rotate the device, the photo is going to rotate, right? So the device is now in landscape left, but in iPhone OS 2.0 and earlier, the Photos application actually didn't rotate the user interface. So the interface actually stayed as portrait, even though the device was now landscape, and even though some of the picture actually rotated. So anyway, all these things are kind of independent, and you can control them independently in your own application. Well, obviously, you can't control the device orientation in your application, but yeah, the interface orientation you can. And Safari does the same thing, except in Safari, it actually rotates the interface. And Photos does now as well as Mail and Notes and pretty much all the apps on the phone in iPhone OS 3.0. So OK, that was kind of a rambling tangent there. Let's get back on track. So let's get the physical device orientation, right? That's the way the user is actually holding their phone. So you do that using the UI device class. You usually want to start notifications by calling begin generating device orientation notifications. Again, we've got these nice long names, so you have to type a lot, or autocomplete. You can start finding out about these things happening by registering for the UI device orientation did change notification. This will get called. The granularity is basically the user has actually fully rotated their device, so it's not called a lot unless the user's like moving back and forth constantly. So it'll be delivered to registered observers. I think we've kind of talked about this briefly. There's the NS Notification Center, which is the class that's used to register for notifications. I don't remember if we really got into that. So if we didn't talk about it yet, or you're not real familiar, does that sound familiar to anyone, actually? Heard about it? No? All right. Well, there's a class called NS Notification Center. And you can use that to register for global sort of app or system-wide notifications. And one of those is going to be this UI device orientation did change notification. You can find that in Foundation in nsnotificationcenter.h. We're not going to get into it too much, but there's really only one method you have to know about there. Well, two. There's register for notification, and you specify an object and a method to be called for that when that notification happens. And then there's unregister, which lets you unregister for unregister for notifications. And then finally, we've got the end generating device orientation notifications, which stops generating these. The interface orientation stuff is, there's kind of two ways to get at that. The UI application class defines the status bar orientation property. And this is always up to date based on where the status bar currently is on the screen. So if you're holding the device in portrait and the status bar is up top, then status bar orientation is UI interface orientation portrait. If the status bar is left and one of the orientations, it'll be landscape left or landscape right. That's on UI application. It defines the orientation again, not the device orientation. So it's the orientation of the interface, which may not be necessarily tied to the orientation of the device. That's kind of, usually you'll use that to get the orientation. You very infrequently will use that to set the orientation. UI View Controller actually provides its own concept of interface orientation, and it updates the application's interface orientation for you. And there's this, actually, it's pretty easy to use. There's a method that you can override in your UI View Controller subclass called should auto-rotate to interface orientation. And it takes one parameter, which is the interface orientation, and the return value is a bool, either yes or no. So if you implement this method, you don't actually have to worry about any of those device methods we just talked about, and you don't really even have to worry about the UI application method. You basically just implement this one method and return yes for any orientations that you want to support. And UI View Controller takes care of the rest. It rotates your interface for you. It updates the status bar location. It handles all that. So you just implement this one method. It's going to rotate everything. If you've set up all your springs and struts in Interface Builder on your view controllers, your view controller's view, things will even relay out correctly and move around. You may actually need to do some more on your own if you actually want significantly different layouts in portrait and landscape. But for the most part, View Controller takes care of all the specifics of this for you, so you don't have to do too much at all. There's a new thing in iPhone OS 3 that lets you detect shake. And shake, by default, is used for undo and redo on iPhone. You can override that yourself in your own applications to mean something else if you want. there's a standard event that gets called that basically guarantees that our definition of shake is consistent across everyone's app. So if you want to say that you have to like shake to shuffle in your card game, it'll be the same shake motion to shuffle that it would be for shaking in any other application. So you probably want to take advantage of our shake event rather than try and write your own based on the raw accelerometer, just because then users won't get confused why what they think is a shake in one app isn't a shake in another. Use ours and it'll be consistent everywhere. So the way you get to this is there's actually well, I don't have the method on here. If you open up UI responder, there's another responder method. I think it's, God, I forget the name of it. Do you guys know off the top of your head the name of the motion event method? Well, anyway, there's a method on UI responder, just like the touch events that we talked about last week for touches began, moved, ended, and canceled. There are also events for motion, and I can't remember them, but you can check it out in uiresponder.h. And the thing that you'll get through these events is a UI event that has type UI event type motion and subtype UI event subtype motion shake. Currently, that is the only subtype defined. So if you get one of these, you pretty much know it's that. But you should still check for it in case we introduce new ones in the future. And basically, this will get passed down to the first responder when the user shakes their device. So that's pretty cool. I mean, it's nice to know what direction the device is in. But what if you want to do something a little more interesting than that? If you really want to, figure out the user's shaking in one direction, or you want something more raw. You don't just want what orientation the device is in. So you just want this. We just want this raw data, right? So in this case, we can find out, what acceleration is happening in different orientations. We want to get that directly and actually process it. So that's where we start to get into this accelerometer interface. It's also part of the UIKit framework. There's a UI accelerometer class. It delivers 3-axis data, so it'll give you X, Y, and Z for all the orientations that you might be interested in. It's got configurable update frequency, so you can sort of get updates either 10 times per second, 100 times per second, sort of tailored to what your app is trying to do. And it's delegate-based event delivery. It's pretty similar to the CL Location Manager class that we already talked about. So you basically end up getting the orientation something like this, right? You've got the Y that's going vertically through the device, X is going horizontally through the device, and then Z is coming out the front and out the back. So the accelerometer interface is the UI accelerometer class. There's a UI acceleration object, which will tell you, about the acceleration at a particular time. And again, a UI accelerometer delegate. So this probably looks pretty familiar. It's basically the same as the CL Location Manager interface. To configure it is slightly different. UI accelerometer, you don't allocate your own. There's a singleton one that you get using UI accelerometer shared accelerometer. You set the update interval so you can pick how frequently you need these updates. And then you set the delegate to yourself. This part's pretty important, actually. There's no begin and end generating updates like there is on CL Location Manager. Just setting the delegate causes the updates to begin. So if you want to disable to save power, the accelerometer, there's no method you call. You just set the delegate back to nil. It's a little odd, but yeah, that's how that works. So yeah, if you're not using the accelerometer data, but you've already set it up, set the delegate back to nil to turn off the accelerometer. Oops. All right, so yeah, event delivery begins as soon as you assign the delegate. All right, so defining your delegate object, right? You've got your accelerometer did accelerate method that you'll implement on the delegate. And that's going to give you back this UI acceleration every time that, well, whatever the frequency that you've asked for the updates are at. And from that, you can get the the acceleration's X, Y, and Z values, which are just floating point values that you can process to do whatever you want with the acceleration. There's only one delegate per application. There's a singleton instance. So if you've got 2 objects in your app that both need acceleration data, you kind of have to multiplex that yourself. So you have to set one object up as the delegate and then hand off the acceleration objects to the other 2 yourself if you need it in 2 places. And these things are delivered asynchronously on the main thread. So they're just queued up as events on the main thread. If your main thread is busy blocked, not receiving or processing events, you're not going to be getting acceleration events because you're blocking the main thread. They're delivered on the main thread, so another reason not to block the user interface. You also won't get acceleration events. So I kind of mentioned the range is sort of somewhere between 10 and 100 hertz. You can get set it up anywhere in between those pretty much. The frequency really should be based on what you need. If you're just trying to detect rotation events, in this case you don't really need to worry about this because we've got all these other APIs for figuring out what orientation the device is in. But if that's the kind of thing you were doing, you don't need to update very frequently for that. 10 or 20 hertz is more than enough. The user's not flipping their phone around in a circle and trying to rotate the interface at that speed. If you're trying to control a game based on that and you really want direct feedback and something to happen right as the user moves the device, you probably want to up that to maybe 30 or 60 hertz to get more frequent input. But even 60 is getting pretty high. That's the frame rate of the device. So you may not even be rendering your game at that speed, depending on how complicated your OpenGL is. Yeah, as I mentioned, to disable the accelerometer events, you have to set the delegate back to nil, which it's a little odd, but keep that in mind as you start using this thing. If you're not needing the accelerometer data right now, set the delegate to nil. Your users will be happy because their device's battery life will last longer. If you want to start filtering some of this data, because we won't get into this too much, because this is more starting to tend towards frequency analysis, and it's kind of beyond the scope of this class. But there's two pretty basic things that we can kind of get at some really simple algorithms for real quickly, and that's a low-pass and a high-pass filter. So a low-pass filter would sort of isolate some constant acceleration. So if you're just holding the device still, but maybe just jiggling a little tiny bit, a low-pass filter would kind of get that jiggle out of there and just sort of show the basic general way that you're holding the device. A high-pass filter would be the thing that we do to allow that jiggle to be seen. You would see just the jiggle and not the stillness. So you use the low-pass filter to sort of get more large-scale changes and smooth out the acceleration data, and the high-pass filter will give you more user-intended movements, like smaller movements, basically. So if we start taking a look at some of this and plotting it on a graph, right? So let's say we're holding the device straight up and down. We're going to see no acceleration in the x or z directions because we're not moving in those directions, and we're holding it straight up and down. So y is going up and down through the device. In this case, you can see in the middle of that graph there, there's a steep drop where it went down. That actually is where we turned on monitoring of acceleration, right? Because we're holding it this way. Since we're on Earth, we got 1g of acceleration because that's what we got. So you can see that right there on the graph. It's actually at -1 because it's pointing downwards. So let's kind of pull that out there. That's our -1g of acceleration. So if we wanted to take that and actually figure out the frequency of it, you'd sort of start wanting to use a Fourier transform. We won't talk about that too much right now. You can kind of, it's more advanced signal processing than what we're going to be talking about here. But the basics of what you'd be doing would be basically converting from the time domain to the frequency domain, right? So the graph on the left is the time domain. We're seeing over time what the acceleration values are. If we convert to the frequency domain, it's basically showing us the frequencies that we're seeing in that graph. So in this case, we're seeing a constant frequency of at 1g, right? But if we start to shake, so let's kind of take our device and start doing that, then we're going to start seeing something different on our time domain. The acceleration is going to start going up and down. But in this case, you can see here, it's actually still centered around the -1g because we still have that acceleration from holding the device vertically. So so now our frequency domain actually shows both of those motions in addition to the standard gravity. So let's say we wanted to isolate just the orientation that we're holding it in, right? So that we just want to isolate that constant force of gravity. In this case, we're going to try and apply a low-pass filter, which will get rid of that, the horizontal movement that we introduced. So we really just want that thing in the middle, the one frequency that was showing where we were originally holding it. So the way we'll do that is with a low-pass filter, which will pass just that low frequency values. There's certainly more complicated ways you could do this kind of thing. This is a super simple example. In this case, our low-pass filter is basically just going to weight the previous value at 9/10 of the new value. So as the value is changing over time, it's going to tend towards whatever the previous value was. So if you're holding, so if your acceleration in this case is 1, just holding it still, and we're just moving it up and down, we're fluctuating between like -0.5 and -1.5 as we move up and down. But we're always sort of centered around that 1. So if we keep if we keep preferring the previous value, we're always going to sort of tend to stay around 1 because the average is always going to be around 1. So the low-pass filter here is basically weight the old value higher than the new value, so that if you're just moving back and forth and still staying around that 1 value, we'll keep preferring that 1 value, basically filtering out that movement of the up and down. That's it's a pretty simple example. There's way more complicated things you could do. This is not intended to be highly complex. All right, so that's basically the low-pass filter case. Let's take a look at the high-pass. So now in that case, we actually want to get rid of that thing in the middle and just look at the movement, the motion of the up and down, right? So if you stop and think about that for a second, we just figured out what the thing in the middle was with the low-pass filter. So all we basically filtered out everything else. But if we start and take the whole thing again, we can basically just subtract off what we just figured out from the original, and that gives us what's left, which is what we want here. So we use the low-pass filter to find that frequency in the middle. So if we take the real frequency and subtract out the value from the low-pass filter, that pretty much leaves us with the high thing. So basically, that's going to be almost the same code we just saw, right? We're going to calculate the low-pass using that low-pass filter, and then get the current raw acceleration and subtract out the low-pass value from that, which is pretty much the high-pass filter rate. It's going to give us the remainder that we didn't already just subtract out. So anyway, that's the kind of the way that you will. It's a very basic way to separate out the low frequency and high frequency movement from your acceleration data. So a pretty good sample or example rather of low-pass filtering is this bubble level app, and I've actually got that over here. So let's take a quick look at that. It's kind of hard to, we can't really do it in the sim, but I can look at my smiling face here for a second. And sorry, smiling face. So if we take a look at the bubble level, sorry, it's flipped horizontally. I can't really fix that. As we tilt it, that bubble starts moving, right? So if we do this real fast, it's not kind of going crazy. We're applying a low-pass filter, so even if I'm like shaking it around a little bit, it's still tending to stay pretty much just with the level of the device. So let's actually look at one other example here. And this one is kind of taking into account both low-pass filtering and high-pass filtering to do something a little bit more interesting. Oops, hang on. I'm shaking my device a little too much. All right. So here we've got, let's take a look at the low-pass filter, which is going to give us the general orientation of the device, right? As we move around, it's going to start moving towards that orientation. But if we then use the high-pass filter to get some high frequencies out, we can start to detect like rapid movement while still kind of aiming towards the low pass to get general orientation. All right.
You said this is using a low pass and a high pass?
Yeah, so it's using both the low pass and high pass. So the low pass filter, the low pass is passing the low frequencies, which is basically the general orientation, right? So that's when it's moving back and forth a little bit. And then the high pass filter gets us like the shaking, the really rapid movement. So that's when the pedals start flying off because you're moving the device real rapidly. So you can figure out what direction you're shaking it in and that it's happening really quickly. Oh, forgot to put the...
Is that demo app? Is it a demo app?
So the first one was a sample. I believe the bubble level sample code. This app is not. And so I have to find out what the story is because I didn't write that, and it's not a sample app. I'm not sure why it's not. I got to see if I can get permission to post it. If I can, we'll get it up on the website. But I know there's been trouble getting that particular one shown in the past. It uses actually an open source physics library to do some of the bouncing back and forth. I'm not entirely sure what the issue was, but I'll look into it and see if we can get it posted. So again, no simulator support for this either. I probably wouldn't want, again, your users like tilting their Mac Pro around trying to get the accelerometer. So yeah, you have to use a device if you want to use any of these acceleration APIs. So a couple of tips for that. Use the UI view controller stuff if you're trying to do orientations. If you just want to rotate your interface, it's a great way. It wraps all the complexity of figuring out low pass, high pass filters and orientation a lot of time was spent, making sure that the device rotates at the right time when the user actually means for it to rotate. So just use UI view controller's auto rotation, and it'll take care of a lot of that for you. If you do want to use raw data, try and use some filters to extract just the parts that you care about from the acceleration, so that you can, ignore the really high frequency movements if you just care about general orientation, or the opposite. And disable the accelerometer updates when you don't need them to preserve power again. Let's see what kind of time we have here. Oop, almost done, huh? All right, so that kind of leads us into the battery and power management, which we'll just kind of talk about real briefly. So again, these are pretty small devices, and as small devices, pretty small batteries. They're very low power. And what do we mean by low power? So laptops, pretty low power, right? I mean, it's a portable device. It's running on a battery. You want it to last for a while. So kind of power is probably about 20 to 60 watts is what a laptop's using. So I don't know, order of magnitude. What do you think iPhone is going to be using? Anyone? 5 watts? All right. Well, sort of, not quite. No. Think less. Here we are. We're going to probably be talking like 500 milliwatts up to maybe 2.5 watts. And when we're saying 2.5 watts, we're talking like we're using the accelerometer, we've got the screen on, we got GPS updates going. We're using the device. More accurate is probably, general usage is around 500 milliwatts. So super low power. And you really want to try and stay down at that low power, the lower end of that spectrum, so that you can keep the device lasting longer, because it's a pretty small power. So there's a couple of techniques that the iPhone uses to kind of maintain the duration of these batteries. One of those is dynamic clocking. It reduces the clock speed of the CPU down to be slower when it's not under heavy load. So in the event that you're not doing a lot and don't have a lot of processing going on, try not to be doing like polling waits on things, because that's going to keep the CPU alive and active, just spinning in a loop waiting for something to happen. Try and use one of the asynchronous non-blocking callbacks so that your app can go back to the kernel and get called back later, because then we can actually put the CPU in a lower power state. We also do a lot of clock gating and power gating. So the idea here is basically blocks on chips that are not in active use will get powered down so that they're not a drain on the rest of the system. So this is kind of where you want to stop using the accelerometer in cases where you don't need acceleration data, because then we can actually power off the entire accelerometer block and it won't draw any power. Yeah, I mean, everything consumes power. The radios are consuming, some amount of power. They're actually the most expensive part. This is kind of listed in order of the expense. And actually, transmitting on the radios is even more expensive than receiving. The CPU and GPU are probably next on the list there, followed down by the display, the hardware modules, and then finally, well, actually, that's it really. But keeping the system awake actually will keep all of these things going. So when the user presses the home button and the screen turns off and the device locks, generally what we want to do at that point is put the system to sleep. We don't want to be actively running the CPU, because we're not actually trying to compute anything at that point. The user's not really trying to use their device. We want to keep minimal systems awake, just like the cell network connection, so we can receive calls, but in a very low power state where we're not doing a lot of transmitting. So you really want to keep in mind that you're on one of these devices and not be running all your different devices at full power when you don't actually need them. So yeah, we got a nice battery picture there. That's what you don't want to have happen. Let's avoid that. So as I said, transmitting is the most. Oh yeah, what's up?
So if your app is processing something and then the user locks the phone, and you're like in the middle of doing a heavy computation, what happens to that?
So the question is, if your app is processing something and the user locks the phone, but you're in the middle of doing a heavy computation, what happens? And the answer is, I should know the answer, and I do not. I think it'll keep going for well, it'll definitely keep going for a while, but I don't know if there's a timeout period on it.
30 seconds.
I don't remember if we forcibly stop it or not. I can check in and get back to you. I don't know off the top of my head. So for the radios, transmitting is the most expensive. So the kinds of things you want to keep in mind when you're doing that are, if you're doing a lot of network requests, try and batch them up all at once. So if you know you're going to send out a request for, or send out 4 blocks of data. Try and do it all at once rather than over some period of time. Also, if you have a choice in protocols when you're picking your network protocol, try and pick ones that are less chatty, that require less transmission, and especially ones that don't require periodic transmission. The network stack tries to shut itself down into a lower power state if it's not in use for a certain period of time. So if you've got a network protocol that requires that you check in with a server like once every 5 seconds, the network stack will never be able to go into a low power state. It's going to be just up and waiting to transmit and receive constantly. So try and use network protocols that are just don't require a lot of communication back and forth. And try and use compact data formats so you can reduce the amount of data that have to get sent. The JSON stuff we talked about is a great example of that. It pretty much captures all the complexity we need to represent all the foundation data types, but it's super compact. There's very, very little overhead in actual descriptive text in the protocol. The majority of it is your actual data, unlike some more verbose XML formats that are just much larger and full of all kinds of descriptive stuff. And also with the core location and the accelerometer, stop generating the location information and the accelerometer events when you don't need them. For core location specifically, if you only just need to know where you are right now, but don't need to know over time where you're going to be, turn it on, get the location, and once you've got the location, turn it back off so that we can power down GPS and all these other devices. So do reduce your CPU usage. This is kind of a double-headed thing for you. If you reduce your CPU usage, your app's going to perform better, so your users are going to like that, and it's going to use less power, so they're going to like that. So using Shark and Sample to figure out where you're spending all your time and optimizing your hot code paths is a great way to both get better performance and increase your battery life. And also try and stress the GPU less for pretty much the same reason. If you have a really, really complicated user interface on screen that's got just like tens and tens of layers all over the place, layers meaning views, every view has a layer, it's significantly more complicated to render than a screen that has maybe only 5 layers. So if you can get away with fewer layers, it's a good way to use the GPU less and conserve power. Writing things to the flash, the NAND, is also very expensive. As I mentioned before, it takes quite a while as well. It also uses quite a bit of power. So if you have a bunch of state that you need to store out persistently, probably don't want to be writing it out like on a timer every second. Try and write it out when it changes. And accelerometer setting delegate to nil. Letting the system sleep we already talked about. So we're about out of time, so that's about it, unless anyone's got any other questions. Yeah?
Can you also access the proximity sensor?
I'm sorry?
The proximity sensor?
The proximity sensor. Can you use the proximity sensor? I do not believe there's an API for using the proximity sensor, no.
Wait, then how does an app like Google Mobile work when you lift the phone to your ear? Because it has this feature where you can lift the phone to your ear and then it beeps, and then you can start talking right away and it'll do a search.
There is no access to the proximity sensor. Yeah. Question is, how do apps like Bump work? And actually, that's just an accelerometer thing, I think. I'm pretty sure that it just detects the motion. And I'm pretty sure that actually, I don't know specifically about Bump.
So
but
Bump's actually coming in this Friday. Yeah. I'm going to talk about their APIs.
Nice.
Bombs coming in?
Yeah, the Friday section is Bump, and they're going to discuss the API if you want to use it in your project.
Yeah, I'll leave it to them to answer rather than make some stuff up about it that I don't really know. OK, thanks, guys.
For more, please visit us at stanford.edu.